Alright, back again with some more fun questions. These will all be kind of long, so I hope you're ready for some more fun. Our statement now reads, a rare case in which the electrostatic field E for a circuit can actually be calculated is the following. Imagine an infinitely long cylindrical sheet of uniform resistivity and radius A. A slot corresponding to the battery is maintained at potential plus or minus V0 over 2 at phi equal plus or minus pi. And a steady current flows over the surface as indicated in the diagram. According to Ohm's law, then, V at A phi is equal to V0 phi over 2 pi, with phi being between negative pi and positive pi. So what we want to do is use separation of variables to determine Vs of phi inside and outside the cylinder. Okay, remember separation of variables for Laplace's equation only work where we don't have any charge, so hence inside and outside, not at the surface. Okay, so then find the find the surface charge density on the cylinder. All right, let's draw it out. So we have plus or minus V0 over 2, again corresponding to plus or minus pi for phi. And we see that the sheet now has some current running over it. Again, radius A. Kind of a weird looking diagram, but take a second to ingest it. So since for part A we want to find the solution via separation of variables, what we need to do is look back to chapter 3 when we found the general solution in cylindrical coordinates. And what we found is that for inside the cylinder, we had the sum for s to the k power, some radius to the k power, ak cosine times k phi plus bk sine k phi. And then again, if we're outside, we still need we need to tend to 0 as we get infinitely large, so hence s to negative k. And so for that, that's the only modification, but again, we have different coefficients for both. Let's put a couple notes here, though. Originally, when we found the general solution, there was an A0 plus B0 ln term found in the solution. This isn't needed here due to matching a form of the given potential, since we were given V0 over 2, things of that nature. Further, what we need to note is that the potential is an odd function of phi, so the cosine terms will drop. Okay, again, this is all trying to match. And again, looking at VA of phi equal V0 phi over 2 pi. So if we're trying to match things up, you know that we're supposed to be odd there, so let's work with that. We're doing this now so that we can save ourselves later, a lot of work later. And then what we say is that S equal A, we have Vn equal V out, which is V0 phi over 2 pi. And so with that, what we're going to do is use Fourier's trick with orthogonality to solve for BK and DK. Should be ringing a bell. We did this plenty in chapter 3. And so if we want to start with the Vn term, let's go ahead and apply these modifications. And what we see is that at S equal A, we have AK, right, instead of SK. Not to be confused with the A sub k for cosine. And then again, we got rid of the cosine, so this goes to BK sine. And then what we're doing is setting it equal to V0 phi over 2 pi. Let's invoke Fourier's trick, where we're integrating from negative pi to pi, sine k prime, and then just work it through. Okay, again, we see orthogonality comes through, so we're canceling here, canceling there. What we see is that we get the Dirac delta. Again, thank you, orthogonality. So what this says is that this only holds if k and k prime are equal. And so what we do is chug it on through. We get a to the k, b to the k, pi. And then as you see here, V0 over 2 pi. Once we evaluate the integral, you get a sine and a cosine with phi. Blah, 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 basic calculus. But what we notice is that with that, when that happens, we get a 2 pi factor because of the phi, and then cosine alternates between -1 and +1. Okay, so that'll be fine there. And we see that the 2 pi's cancel, And what we're able to do is divide over the A and pi. And we see that we solve by solving for bk, we get negative v0 over pi k times negative 1 over a to the k power. All right, so that's how we find our coefficient. And we'll go ahead and plug that through. V0 over pi, negative is all constant, so we just plug it through the sum. No need to worry there. All right, and then here, since we're just, we have a power to k, we just simplify everything down. So we have 1 over k minus s over a to the k sine k phi. And then with the similar method, what we did was find v out. So again, all we see is that we're pretty symmetrical here, except for the fraction flips, as you might expect, because again, we have to die out at infinity. So s is in the denominator there. All right. So what we want to do now is that both sums are of the form s equal sigma, big sigma, infinity to k equal 1, and 1 over k minus x to the k power sine k phi, where x is equal to s over a for s less than a, and a over s for s greater than a. This series can be summed explicitly using Euler's formula. Okay, here you might think there's a lot of hand-wavy stuff, but in complex analysis, there's a lot of work done with these to be able to condense these sums. You have several series like Lorentz series and other things like that that could help you with this. This is just an application of the things that we see in complex analysis, so I would reference you to that if you get stuck here. But basically what we're trying to say is that, look, we can solve for an exponential, which is easy to multiply and divide with. And we're doing that solely so we can simplify this down later. So here we have the sum as the imaginary part of the exponential, since all we want is signs. And then we could factor a k out, combine it all to one thing. This is actually an expression of ln in the form of ln 1 plus w, again, which is matched from expansions that we've seen before, hence putting the two things together. And then what we see is that s is equal to negative the imaginary component of ln of 1 plus x to the e to the I phi. And then here, what we also need to note is that the ln of the complex exponential are r e I theta, which is a definition, is equal to ln r plus I sine, or I theta, because we can expand it and then use log properties. So what we want to say here is that s is actually equal, negative s is actually equal to theta if in comparison to it. And we know we can find theta from the tangent function, because we know that tangent is equal to the sine over cosine, which is equal to the imaginary part of this thing over the real part, going back to the exponential that we had. And remember that the exponential led to the natural log, and so we're going backwards. The natural log is now the exponential. And what we see is that the imaginary part is sine, the real part is cosine, so this works out. Passing this on, what we see here is that tangent of theta is equal to x sine phi over 1 plus x cosine phi. So if we solve for theta, we get this thing, which again we proved earlier was equal to negative s. Once we put all those together, we can now state explicitly what the potential is inside and outside in terms of a function without a sum, mind you. That was the whole goal, is to get rid of the sum. And so we do that here. Again, they look very symmetric, but they're kind of flip-flopped with A and S, so to speak. So be mindful of that. Again, I would highly recommend you go look at a complex analysis text if you need to. These sums and series can be used or found in many tables as well, but it definitely is a headache to try to contemplate how to get there. All right, so for part 2, the surface charge we know was a boundary condition. So with that, we need to find the normal derivatives at s equal a for v out and v in, okay, which is stated there. So take the derivative of v out, messy, simplify it down, okay. And then what we see here is same thing. V in, take the derivative, cancel. We like the cancelings. Yeah, it's pretty fun, but definitely messy. Once we cancel that and simplify it, we see that Vn is equal to minus V out, which is equal to V0 over 2a pi bracket sine phi over 1 plus cosine phi. Again, be very careful there. Just simplify, use the rules of algebra that you know. And then once we do that, we can factor out the V0 2a pi with the epsilon naught, cancel the 2, cancel the negative, and then we're left with the sign, that bracket. And so once we do that, we can simplify it down to epsilon naught V0 over a pi sine over 1 plus cosine phi. And then if we really want to be special, we know that we can substitute in a tangent half angle identity, and that's what we do to sum it up nicely. But there was a big part of that problem was knowing how to deal with the series solutions that we find, and that's going to be a problem with a lot of textbooks and a lot of things to see in physics. So it'd be worth investing in it.